Alright, so I'm going to continue on with my spreadsheet, and after thinking about it, we'll see if there's a more efficient way to set this spreadsheet up. But I have columns right now for the regular stress, deviatoric stress, and then the total elastic and the total plastic strains. We're also going to need some place to put the increment of elastic and plastic strains. So let me see here. The increment of elastic strain, if we have a constant increment of stress, the increment of plastic strain of elastic strain will be the same. The increment of plastic strain is what we're going to calculate, and that's going to be different. Let's see here. I think what I'm going to have to do is I'm going to have to make a separate set of columns here. Maybe it's better if I use the separate spreadsheet, but I need to either insert into here, probably that's the best thing to do, is to insert into here some more columns where we have increments of these quantities. Let me copy, and I'm just going to paste them into here. Okay, we'll fix the error here in a minute. But now I'm going to go ahead and just make all of these quantities D terms. And I'll do the same thing for the plastic strains. We'll go back and we'll resize the columns and we'll change the colors here in a moment. You know, this may be kind of painful to watch through some of this, but you can speed the time up a little bit. But I do think it's important to go through all of these steps, because you know, if I leave anything out, it'll be something that somebody has some questions about. Okay, so let's see here. Let's change this color to make sure we don't confuse it with the total strains. Hopefully that's not too bright. In fact, to keep the things looking similar, let's use a similar green and then a similar blue. We'll use a little softer blue for these increments. Okay. Alright, so our current stress state is right here. And I'm just going to copy that all into here. Let's see what's wrong with this one. Okay, that's taken the 0.3 Let me fix that. Okay, so I didn't want to multiply this by the 0.3, so we'll fix that from the previous spreadsheet. Alright, so there's my starting stress location, and we'll take these values, or these formulas I guess, and we can paste them in here. They should be our starting deviatoric stresses. Our increment of elastic strain is going to be based on the increment of stress that we're taking to the next stage. So this will be the 150. In fact, we ought to probably do these values plus the increment. Okay, so the 150, we know what our total strains are. Well, let's get it on one line. This is kind of where it gets to be a little bit confusing. We're going to take this, and this will be our values here. Let's see what's the matter here. I need some more dollar sign somewhere. I need a dollar sign on the one of these other terms. Let's see. Took those, all right. Let's see. Did I get off on the wrong row? I did. So in this formula, I got off onto the wrong row. I should have had a D. No, that would be a C8. All right. So, need to fix a couple things here on my previous iteration. Okay, so now I'm on the right line. All right. So here's my starting stress. Here is my starting strain. My plastic strain is all 0 when I'm right on the yield surface. And then my total strain let's set up the symbols for that. I'll get rid of the subscript here. And let's change these colors. It's going to be the elastic plus the plastic. Okay. Let's get a little bit wider column here. There it is, 225. All right, so I'm in a uniaxial state of stress, so I get a uniaxial state of strain, and I have Poisson contractions in the other two directions. So I think I have everything set up. Now what we're going to do is we're going to take a fixed increment of stress and we're going to add that to this stress state. So this one down here is going to be this value plus, and we're going to do a dollar sign on the 10. And I should be able to paste that into here. All right. So if I update my stress tensor, I can use my same spreadsheet. I'm going to calculate the trace if I want to do that. I can update those formulas. My increment of elastic strain, let's fix that. So this is going to the next level of stress, is going to depend on this value, B13. And F13 and J13. No, this is the increment. All right. It's going to be B10. F10 and J10. All right. The increment of elastic strain is the same for each increment if we use a fixed incrementation. Let's copy this formula. We're going to do what we did before. Let's go over to the 2-2 term. And it's going to be F and B swapped. Oops. F and B swapped. And over here, it's going to be the J and the B swapped. And this is going to be C10. Now, since we're dealing with a fixed increment of stress, I'm going to put a dollar sign on those terms. And to do that, I'm hitting the F4 button. That's something that I recently learned from one of my students. Now, if you're not using fixed incrementation, you have to be a little more careful here. All right, so let's make a little sketch to talk about what we're doing. So here we are in our deviatoric stress space. And we went from here to here in one big jump. And we're sitting here, and we're going to add an increment of ds. It comes from an increment of d sigma. So we said the d sigma was the big delta sigma over whatever number of increments that we wanted to use. So we're starting with our elastic strain. Now, we want to calculate the strains. Our strain at this spot, at this new point, is going to be equal to next increment is going to be equal to the strain on the surface that's calculated from the elastic portion plus a d epsilon elastic, and here's the part that's really of concern for our class, the d epsilon plastic. All right, so let's take a look at our equations to calculate plastic strains from an increment of stress. First of all, we need to make sure we have a loading increment. So we need to go through and we need to do the n dot d sigma, and we need to see if that is greater than 0. It is in this case, so I'm not going to make a big deal about it. If you have a more general plasticity algorithm you are coding up, you need to make sure that that is indeed the case. All right, so let's get our formula sheet over here. Again, for J2 plasticity theory, we're going to be using this normality flow rule. The epsilon p is equal to d lambda n dot d sigma n. Let's write that down. D epsilon plastic is equal to d lambda n dot d sigma times n. Now, we've gone, n is a unit normal. Okay, so at this point, n is a unit normal. We've gone through and we've shown that the n in regular stress space is equal to the n in the deviatoric stress space. All right, so we're good there. We've also gone through the process of showing that n dot d sigma let me back that up. We're also going to be able to express n dot d sigma as a summation, but that can also be expressed in the deviatoric stress space due to the summation here. All right, so let's talk about n in the deviatoric and regular stress space. N in the deviatoric stress space is a unit normal from the point going outward, normal to the yield surface. If we have a function, if we take the partial derivative of that function with respect to its components, that gives me a vector that's in the direction of that unit normal. Right now, this is not a unit normal. If we want to turn that into a unit normal, we need to divide it by its magnitude. So if we want to say the components of a unit normal nij would be the partial of f with respect to sij, we need to divide it by its magnitude, which is the square root of this thing dotted with itself. Right, for the J2 flow theory, our yield function f is 1/2 Sij Sij I'll do it this way, minus k squared. It's equal to 0. This term right here, Sij Sij, is like Smin, Smin. Those are number indices that represents a summation. So if I were to expand this out, this would look like S11 squared plus S12 squared plus S13 squared plus all the way down to S33 squared, and then we got minus k squared is equal to 0. If I were to take the partial derivative of f with respect to any one of these components, for example the 1 component, then I would get the 1/2 from out in front, I would get the 2 from the exponent, and then I would get the 1, 1. And likewise, any of these would result in that term. It's unique to this particular setup. If you have a different yield function, it doesn't work out that way. You just have to do the math. In this case, it works out that way. All right, so what is Nij then? It's equal to partial of f with respect to Sij, which happens to be Sij. And then we have square root of partial of f with respect to Smn, the partial of f with respect to Smn, which works out to be Smn Smn. Now here's where it gets to be, I think, kind of neat. What is Smn Smn? Well, if we look at our original yield function up here, 1/2 Smn, remember these are dummy indices so I can freely replace them. It's equal to 2k squared. But we've also seen what k is equal to. K is equal to sigma naught squared over 3. Okay, so I can really express, in the case of J2 plasticity theory for isotropic materials, with that. Now, sigma naught, we have to be careful. That's the current von Mises stress. Since we're doing isotropic hardening, we have to make a note of that. That term is going to be updated. All right, so let's see. Let's save this page. Let's see where we're at. Let me get rid of some stuff here. Let's go back and write down our equation. For d epsilon p is equal to d lambda n dot d sigma times n. So what do we have right now? D epsilon ij plastic is equal to d lambda. I'm going to write it like this. I'm going to kind of mix some of my notation. N dot d sigma. And then I have the Nij right here. So this term, I think we can update that. Let's see here. I forgot the square root. So sorry about that. I forgot the square root. The n in this dot product is this term dotted with d sigma, so we can do the index notation, d sigma mn, and then we have our nij, which is our sij divided by the square root of 2/3 sigma naught. Smn times d sigma mn, we've gone through and we've shown that's the same as Smn dsmn. So now we have d epsilon ij plastic is equal to d lambda we have an Smn dsmn, we have an Sij, and then we combine these terms, it's 2/3 sigma naught squared on the bottom, or sigma naught is a current yield stress. We've gone through in class and using our uniaxial theory, I guess, well, let's do it now. There won't be any harm to do that now. We can figure out what d lambda is. Let me save this page. So with a uniaxial state of stress, we can figure out what d lambda is equal to. If we look at d epsilon x plastic, that will be equal to d lambda, and then we will have the corresponding deviatoric stress state. And the corresponding increment of deviatoric stress. Oops. Should be d sigma naught. Actually, since it's a uniaxial stress state, it's going to be d sigma x. Alright, so what do we have here? We have the S vector, S tensor dotted with the ds tensor. So we're going to have 4/9 sigma naught d sigma x. We're going to have a plus 1/9 sigma naught d sigma x, and we're going to have another plus 1/9 sigma naught d sigma x. We're going to have s x, which is 2/3 sigma naught, and we're going to divide all that by 2/3 sigma naught squared. Okay, let's see if we can simplify this down a little bit. We have 4, 5, 6/9 divided by 3, that's 2/3 sigma naught, it's a times symbol there, two-thirds sigma naught d sigma x times 2/3 sigma naught, and we're dividing it by 2/3 sigma naught squared. Alright, so the sigma naughts and those will all cancel out. One of these will cancel out. And if we solve for d lambda, we're going to get 3/2 d epsilon x plastic over d sigma x. Now, we're going to define the plastic tangent modulus as d sigma x by d epsilon x plastic. So that means that d lambda is 3/2 1 over h. Where if we look at our stress versus plastic strain curve, that slope is h, the rise over the run. Alright, so I did all that so I can find out what my h is equal to. Now let's see what h is for the Rhino-Gaussian equation. Alright, so here we are with h. And let's see. A Rhino-Gaussian equation looks like this. In terms of total strain, epsilon xp is equal to sigma over k to the 1 over n. If I rearrange this though, if I want sigma as a function of epsilon plastic, it would be epsilon x plastic to the n times k. So the derivative of sigma x with respect to d epsilon x plastic, okay, we have that, we have an exponent, we have this, the n minus 1 power. Okay. So we have that, but we can also do some manipulations with this term as well. If we want it all written in terms of stress, this would be k in sigma x over k, and then this quantity to the 1 over n, so this would be n minus 1 over n. Alright, so this is what the formula we're going to use for h when we're using our Rhino-Gaussian material. Alright, let's see if we can remember where we're at now. We had d epsilon tensor plastic is equal to d lambda n dot d sigma times n, and then expressed in terms of deviatoric stresses, we have d lambda, which we said was 3/2 1 over h. And before I mess anything up, let me make sure I look at my notes. Probably best if I just go back and bring up that page. Let's see here. So we can use this form, SMN DSMN times Sij divided by 2/3 sigma naught squared. Alright, so here we've got a 3/2 and a 2/3. I guess we can combine those, but let's just kind of carry it through, and we'll worry about that later. Right. So here, this is the current Mises stress. And that is also what goes in here to determine the plastic tangent modulus for a multi-axial stress state. Alright, so I'm going to save this page, and then we're going to punch in our equations into our spreadsheet. So, where are we at? We're going to calculate our d epsilon plastic. And to do that, I'm going to insert some columns so that we have all of our good stuff that we need. Alright, so I'm going to call this one H. So the H that I'm going to use is dependent on the stress state before I take my stress increment. So it's going to be based on these values right here. I'm also going to need a sigma naught, which is going to be our von Mises stress. All right, so let's do our von Mises stress. So here, this von Mises stress is going to be, let's write down the von Mises equation so we don't mess that up. Over the square root of 2. We can do this with J2 as well, but 6 1/2 dozen of the other. Sigma x. Well, I'll tell you what. It's probably easier if we do it with J2. So let's write that down. Get rid of this. One-half Sij is equal to 2k squared, which is going to be equal to 2/3 sigma naught squared. So sigma naught is going to be equal to, Sij is equal to 2k squared. So we have 3/2 Sij, and we're going to take the square root. We'll just make sure that that's right. Yeah, k squared is equal to sigma naught squared over 3. So if I solve for sigma naught, 3/2 Sij, okay. All right. So that's how we're going to calculate sigma naught. So now I'm going to go, let's do this. We'll put in some brackets later, but let me find my previous deviatoric stress state. That's going to be these values here. So I need to do this squared plus this one squared, oops, plus, and so forth. Take all of that, multiply it by 3, divide it by 2, and then take all of that, take the square root. Now the plastic tangent modulus is our formula that we have boxed in. So I'm going to take this and put that in. Plus k times n times sigma O over k to the n minus 1 over n power. And let me just put some brackets here. Okay. Should be a pretty stiff value. We're starting off kind of stiff. Alright, now I need my SMN times my DSMN. Alright, so I'm going to go to my deviatoric stress, my previous one. I'm going to take that times the increment and so forth. Since the increment is fixed for my calculations, we're good. Alright, let's check it out. Let's make sure I'm doing it right. This one times this one. This one times that one, and so forth. Alright. Now I'm going to collect my other terms here, which is going to be my, since I have a 3/2, 3 divided by 2, that's going to be over 2 divided by 3. And then I have a sigma naught squared on the bottom. Alright. So the only thing left to calculate the plastic strains is the D epsilon 11 would be S11. Alright, so I'm going to do, so let me show this over here. So D epsilon 11 plastic would be 3/2 1 over H SMN D SMN divided by 2/3 sigma naught squared, and then I have the S11 term that would go here. So I have all these other things pre-computed. So I'm going to take let's make one more column. And I'll combine everything except for the S11, S22 term, and so forth. So, alright. The other terms divided by the plastic tangent modulus times this term and that should be all I need because I've already taken care of the sigma naught squared. So all of those are fixed for all the increments of plastic strain. So now all I got to do is take this value and I'm going to put a $sign on the 13, and I'm going to take and I'm going to multiply that by my previous value of S11, and yep, okay. Something went wrong because I should have gotten a little bit of 2,2 plastic strain and 3,3 plastic strain. Let me check my formulas out. Okay, something didn't stay fixed. So maybe I put the $sign on the wrong term. Okay, so that looks better. 2,2 and 3,3 should be the same. I'm going to save the spreadsheet. It's all in the setup. Okay, so I've calculated an increment of elastic strain, an increment of plastic strain. And really what I want is the total strains. So, I mean, I could do, I'm going to do this, let's see. Yeah, alright, let's, we're going to take where we are currently at, and we're going to add the increment of the newly calculated elastic strains. So we're going to take this one and add it to this one. So we got a little more elastic strain, and we should be able to just paste this in here. Okay, now our total plastic strain is going to be this one plus the increment of plastic strain that we just calculated. And we should be able to take this and paste this across here. And then our total strain at the new increment is going to be this one and that one. Alright, so this one and that one, I'm not being terribly descriptive, but I think you see what I mean when I'm putting these things in here. Alright, now I think we're set up to do a major copy and paste. Let's get rid of this. Let's do this one line at a time first. Okay, there's our next total stress increment, stress state, rather. There's our next deviatoric stress state. These ought to stay the same. These ought to get updated. Gaussian update in plastic strain increments, giving us a new elastic strain state in plastic strain state in total strain state. And I think everything's looking okay. So what I'm going to do next is I'm going to take this entire thing here and we're going to paste it down. We said 100 increments, so I ought to be, I think, at 111, something like that. 110, 111. Let's see if we get down to 500, maybe one more here, a couple more. Alright, so here's the moment of truth. What I'm going to do is I'm going to plot the values for epsilon x and total plastic strain. So we can find our headings. So let's make a new thing here. Let's go comparison. And if it doesn't work out, I'll have to find my issue, but I'm going to take this from my Ramberg-Gaussian equation. And the total strain. And I'm going to compare that to, I'm starting at 150. These values let's see, paste values, and this one. Alright, now I'm going to make a graph. first graph, I'm going to put the strains from the Ramberg-Osgood equation in here. And the stresses. Let's make sure that plot looks okay. What happened here? Alright, I'm not sure exactly what happened. I must have pasted something wrong. And now we're going to add a series where we use these values of total strain and we use these values of stress. And let's see what we look like. Oh no! So let's see. They don't fly on top of each other. Let's see what happened here. Something seems kind of weird because I know we have a lot higher stresses, so I must not have collected all the plastic strains. Let me check this. Oh, you know what? I didn't start up at the top. So maybe this will fix it. And I need to edit my data series here. So we go down to 104. Alright, there we go. And so that actually looks pretty good. So here is a comparison of our input with the Ramberg-Osgood equation and our output using J2 flow theory, incremental plasticity in the orange. You see we're a little off at the high end. That can be explained by taking the next increment. That can be explained by taking the initial tangent modulus. There are ways you can do to soften that up a little bit, and you can get these strains to pull closer together. Alright, so I'm going to call that a success, and thanks for your patience while I fumbled around in Excel. But what you need to do then for your midterm problem, if you followed along with what I've done, is just do something very, very similar. It really takes putting all these equations together and having a good understanding of what you're doing in order to do this kind of calculation. And you can do it, and I really think this will be a good learning experience when you put all these things together.